Recording in progress.
Good morning, everyone. I'm the chair of the committee today. I'd like to introduce you first to the IFES PhD student, David Abella, who will present today his thesis entitled Aging and Memory Effects in Social and Economic Dynamics, presented under the guidance of Professor Jose Ramasco and Professor Maxi San Miguel. I'd also like to introduce you to the committee. My name is Professor James Gleeson. I'm from the University of Limerick. This is Professor Yamir Moreno from BIFI in Zaragoza and Sentai Institute in Turin, and Professor Caterina Veron from Wrocław University of Science and Technology. I'll remind you, please, not to applaud after the candidate's presentation, as the examination is still in progress. And before the questions of the committee, following the presentation, there will be an opportunity for you to exit the room if you desire to do so. All that said, I'm happy to pass the floor to PhD student David for the oral presentation.
Okay, thank you very much. Well, in this presentation, first I will start introducing the main topics and motivation of this thesis, and then we will go to the two main parts of results. The first about aging in threshold models, we will see what that is, and then to a real case scenario in which we analyze the housing market dynamics. And finally, we will go to the conclusions and further work that one can extract from this thesis. So going first to the motivation of this thesis, actually the motivation of this thesis is to understand how the human activity patterns, how the way we interact affects into collective social or economic systems. So for example, in the formation of a riot that we can see on the image, or for example, in a traffic jam, the way we interact, the way the timing of our interactions happen, affect to the emergent social collective phenomena or economic. But obviously there is an underneath question to that, that is, well, how we humans interact, how is the timing of those interactions? And it has been shown from data from Twitter or phone calls or emails or messaging that actually humans' interactions are not at constant rate. Actually, it's something that happens with a phenomenon called burstiness. And to understand this, I have an example here. This is the timeline of my PhD thesis, and each horizontal line is one of the emails exchanged between me and my supervisors. And as you can see, obviously, emails are not happening at constant rate. What you see is some clusters, a lot of events happening together. So a lot of emailing, for example, for the PhD when we were preparing the manuscript, but also followed by long periods with no activity, with no exchanging emails. This phenomenon is called burstiness and can be characterized by the interval time distributions that we see in the different technologies that, as you see, well, the interval time is the time between different events, between different communications happening, different interactions, and you see that there are a lot of interval times very short, so all events happening together, but also very long periods of time with no activity. In order to model this, one can, in a network of social interactions where each element is an agent, you can say that this is a property of the interactions. So the burstiness is in the interactions. Each time two people decide to connect, and this can be modeled via temporal networks or, for example, traffic flow. Or you can say that this is a property of the agents, are the agents that are activating following this burstiness, and they attempt to interact with others when they get active. And this can be modeled via timers to set to the agents, or potentials, or what we will discuss here, that is the term of aging. Before introducing the term of aging, let me quote what once said the Nobel Prize Daniel Kahneman, that he said that a theory of choice that completely ignores feelings such as pain of losses or regret of mistakes is not just descriptively unrealistic, it also leads to prescriptions that do not maximize the utility of the outcomes as they are experienced. So we actually need to introduce memory when we are talking to human interactions. We need to introduce this past exposure to mistakes. And with this motivation, we introduce the term of aging. Aging can be understood in many ways in literature, but by aging, we mean that the longer an agent has been in a current state, the longer he has been with a certain idea, with some thought, with some habit, the more reluctant becomes to change it. So it takes a cost for you to change your current state. And the cool thing about aging is that it's a simple mechanism in which you can set just an internal time to the agents, that is this time that they have been in the current state, that we may refer to it as age. And now, if you set that the agents will attempt to interact with a probability inversely proportional to this internal time, what you will recover in the interval times are these power law distributions that we see in real systems. So this is the motivation. Obviously, this idea of aging, well, was introduced before us in this paper, in which they took the inspiration from the time-dependent response of a spin glass to a given perturbation. But actually, this idea of aging is something that is very human, because we tend to stick to our habits, we tend to stick to our beliefs, and this is something that has been also studied in psychologist and sociologist literature. But on the other hand, when we try to model social interactions, for example, with the Botter model of social limitation or with the majority vote model, actually we are always assuming that events are occurring at a constant rate or using random asynchronous update. But is this assumption, well, you can say, is this assumption valid? Can you do it and actually nothing happens? Well, in the context of the Botter model, that, as I said, this is a model of social imitation. You just imitate one of your peers. While consensus is not reached and the thermodynamic limit in the original Botter model, you're doing random asynchronous update. When you introduce this idea of aging, what you see is that some coarsening appears, and it is able to lead the system to consensus. So this effect is actually important. Not only that, but it is able for the noisy Botter model, when you introduce noise also to agents, this independent behavior. You can see that you can go from a finite size discontinuous transition to a continuous transition that falls into the Ising universality class. So with this motivation, seeing this that is happening into the Botter model, that is a model of simple interactions, we were wondering what would happen to aging when you have threshold models where you interact with multiple peers, with all of your peers, and see what is this effect of aging and peer pressure in the system. So that is why we went to we go to the first part of the results. And in this part, we actually analyze 3 types of different threshold models: the Sakoda-Schelling segregation model, the Granovetter-Batz, that is a complex contagion model, and the symmetrical threshold model, that is a consensus model. Going to the first one, well, defining segregation is something complicated, but by segregation we mean this formation of bulbs of people that tend to cluster together because they share the same ethnicity or the same amount of money. And the first attempt to model this with a model of social phenomena was done by James Sakoda and later by Thomas Schelling, in which, well, they pick a chessboard and you have agents of 2 kinds. And each time that an agent will see to the neighborhood, and if he sees a fraction of different kind neighbors exceeding the threshold, that here the threshold is the tolerance, he will be unsatisfied and will move to one of the satisfying locations in the system. And what this model shows is that you don't need very intolerant people to get segregation. Actually, with mild values of the tolerance, you already get segregation. And this is a very robust result that you can, that in literature, there are many variants of the Schelling model. One that we analyze is the noisy constraint Sakoda-Schelling model, where now the rules are the following. You have all agents that will move to satisfying vacancies. So unsatisfied will move to satisfied as before, but also satisfied move to satisfied, introducing the noisy behavior of the model. And they discovered that with these simple rules, you have a very rich phase diagram. Here is the tolerance versus the percentage of vacancies in the system. And you have frozen phase, segregated phase, mixed phase. So to this model is the one that we will introduce these ideas of aging. Aging now here is understood as certain emotional or economic attachment to your location. So the longer you have been in a current location, the less you want to change, because you get used to the schools, you get an attachment to the schools, to the public goods, and as long as you have been satisfied in that location, why do you need to move out? So the rules are the same as before. All agents will move to satisfying vacancies, but satisfied agents will move to other satisfying locations with this probability inversely proportional to the internal time, to the time that they have been in the current location. And we will analyze just this part of the phase diagram because we are not interested in large values of the percentage of vacancies, in which we have a transition from a frozen to segregated state and from a segregated to a mixed one. So actually what you have is something like that. The frozen segregated phase, frozen is a frozen state at the end. A segregated is a dynamically active segregated state, and this is a dynamically active mixed state. The transition from frozen to segregated depends on the value of the percentage of vacancies, while segregated to mixed does not depend. And this can be characterized with this segregation coefficient. What happens when we introduce this mechanism of aging? That actually, if it is making you to stay on your personal location, it makes sense that it will go against ordering. Well, actually, what we see is that while the frozen segregated transition is the same, occur at the same values, we don't have a segregated mixed transition, and actually we have segregated values for very large values of the tolerance, where the system is very tolerant. We have a situation like this. The frozen state seems to be the same, but there is more segregation. So in this sense, aging is favoring segregation, which was something unexpected a priori. Not only that, but it is also maximizing the it's not working. It's maximizing the number of satisfied agents in the system, because the fraction of unsatisfied is always lower for the model with aging. That is the blue line here. But on the other hand, as you can see from the animations, here the segregated state is reached very fast. But now here, even though the final segregated state, because this is in the stationary, the stationary state is reached and is the same, you see that there are actually very slow dynamics in here, because the fully segregated state is not reached yet. I will try to fix that. Wow. No pasa nada. Okay. So when you analyze the dynamics, what you see is that the average interface density, so it's like the size of the interface between the two clusters, while for the original model, it follows a decay with a power law with exponent with negative exponent 0.5. This is for the segregated phase, and this is for the mixed phase values of the tolerance. When you introduce aging, it's true that this mixed phase now goes to ordering, but the ordering is much slower when you compare the exponent. Actually, well, you need to look to the x-axis to differentiate. So aging is favoring segregation in the sense that a new coarsening appears in a mixed phase, but the dynamics are much slower when compared to the final with the segregated phase. So as I said, this effect of aging favoring segregation is similar to the Butter model, as we saw before, but now we have this present of long-lived clusters growing in the system. Also, in this project, we also analyzed that aging, well, as we had these long-lived dynamics, these very slow dynamics, we saw that it has some similarities with an spin glass, and we analyzed that we found out that the time translational invariance was broken due to aging. And the results of this part were published in scientific reports in this reference here. So we decided, okay, it's worth to study threshold models with aging. So we went to the Granovetter-Batz threshold model. That is actually a very simple model that has been used a lot to describe, for example, rumor spreading, or the formation of a riot, or the example that I like the most, the innovation adoption, as we have seen a lot of adoption of ChatGPT in these recent years. Well, all of these processes have in common that you need a multiple exposure to the contagion and multiple exposure to the adoption, like to the innovation, for example, in order to adopt the technology. So what is called the complex contagion. And it also has been shown that from few imitators, actually this starts to spread very fast to the system, creating these very fast cascades of adoption. The first attempt to describe this was by Mark Granovetter, and later by Duncan Batts, where he described it more in a mathematical way. And well, what you have is a network of social interactions, and a few agents start to innovate and use, for example, the innovation that is ChatGPT. And this innovation will spread through the system to the non-adopters. So it's an asymmetric spreading, an asymmetric model. And they will do just if they see a fraction of neighbors adopters exceeding the threshold. So if you see a fraction of adopters exceeding your personal threshold, you will adopt the technology. And this leads to the cascade of adoption. And we introduce aging to this model with the following motivation. Now picture you have a scenario of, for example, programmers, and they have a social network, and they have been using Fortran, the programming language, for a very long time. Because Fortran, as we know, is the best of the programming language, according to The Simpsons. And they have been using it for a very long time. They have a lot of code built, and suddenly Python appears in the system, and some of them decide to innovate. Obviously now, well, the ones that have just learned Fortran, they can switch to Python, and it's just learning a little bit a new programming language. But the ones that have been using it for a long time, they have a lot of code built, and it has a cost to change. So it makes sense that agents will now activate with a probability inversely proportional to the time that they have been using the previous technology. And then if the fraction of neighbors exceeds the threshold, you fulfill the threshold condition, you will adopt the new technology. And with this setting, we will ask ourselves, okay, now how aging does modify the cascade condition? How does it modify the cascade dynamics? And more importantly, now that we have a simpler scenario than in the Schelling model, is there a mathematical way in which we can describe this behavior? Well, actually, from simulations, what you see is that first, this cascade condition, this discontinuous transition from a situation where there are global cascades and no cascades, here is the average degree versus the threshold for Erdős-Rényi networks. Well, actually, the discontinuous transition is the same. Aging does not modify this transition. So something different than for the segregation model regarding to the phase diagram. On the other hand, what you have is that when you look to the number of adopters increasing with time, what you see is that the exponential, for the original model, you have an exponential very fast cascade that is replaced now by a power law increase at the beginning, obviously, then it saturates on the number of adopters. So in this sense, now the only effect that we appreciate from aging is that now aging is going against the fully consensus, reaching the fully adopted state, full consensus. So something that is against our intuition that we had from before. And well, going to the second question, to the mathematical description, what we saw is that for describing just the original Granovetter-Batts model, what you need is actually high accuracy, because you cannot use just mean field, or even some cases you cannot use paired approximation, and you need to go to high accuracy approximations. And we used this framework that was developed by one of our jurists here, that I will briefly introduce. When you have binary state dynamics, actually you have, well, for example, nodes in -1 or +1 that could be adopters or non-adopters on any binary state dynamics. You can describe your update rules of the model as transitions between this set of variables that are the fraction of, for example, here is the fraction of nodes in state +1 that have degree k and m neighbors in state -1. So now the node will change the state as following these rates t plus and t minus, and it can remain to its state and actually change the number of links. Following, this change of the neighbors will happen proportional to this time-dependent rate that you can rewrite in terms of the variables, the original variables. You can do this for all the different change of links. And what you get is that for any binary state model in complex networks, you can rewrite your model in terms of these transitions, and then write the so-called approximate master equation. And this is a very good framework because it's very general. As I said before, it's valid for networks constructed with a configuration model according to a degree distribution in the limit of infinite size. But obviously here, what you have is, this is for Markovian dynamics. But what happens when you have non-Markovianity associated with aging? That is the scenario that we have here. Well, what we did is to go from this non-Markovian situation to a Markovian description by enlarging the number of variables. And so now we will define the transitions in terms of the sets of the fraction of nodes in state +1 that have degree k, m neighbors in state -1, and have tau that have been tau time steps in the current state. So as before, you can define the transition rates. Now nodes will change the state and also reset the age, because if not, the age is not the time that they have been in the current state. With this t plus t minus, you can have the same as before for the links, but now you need to take into account these variables, also having into account the tau. And for the aging probability, what you see is that also now a node can remain in its state and age with some rate. And well, we also introduced that a node can remain at its state, but also reset the internal time. That this was actually for exogenous aging, that was something done during the thesis, but was not reported. Well, it won't be mentioned during this presentation. So now with these transition rates, what you have is that the situation that we had before for the approximate master equation gets to a little bit more complicated scenario, in which we have a much number of transitions, but as before, since the only thing that we did is enlarging the number of variables, you have that it can be done. It's also general for any binary state dynamics with non-Markovian features associated with aging. It's also valid for any network with any degree distribution. So we have everything. Well, actually, thanks that for the case of the Granovetter-Batz model with aging, we have many transition rates that are 0, and actually this complicated situation goes just into this simpler case of transitions. And now what you can have is solve this equation numerically with the standard methods, and extract from there how the number of adopters increase with time. And you see that actually the approximate master equation gives you some good results for many different networks. But still, we were wondering, well, but we see that you can fit from simulations that we have an exponential behavior turning into a power law. So what is happening here? How can we describe this exponential going to power law? Well, assuming this kind of solutions, you can reduce the approximate master equation in the derivation on the original paper into just a reduction into a system of two variables, a system of equations of two variables. Well, now aging is just introduced into this term. So now you can go to analyze the cascade condition and actually see that obviously it cannot be affected by aging, because aging is just in this term here, and it's always positive. So the cascade condition is actually this one. So it's the same, doesn't matter how you put the aging. Also, doing a first order approximation, you can see that for the original model, if aging is not introduced, you have an initial exponential cascade with an exponent alpha. And when you introduce aging, this exponential cascade is replaced by a power law, and with an exponent delta, and delta and alpha are found to be the same, and actually follow this simple equation where you have here the threshold and the degree distribution of the network. And it was also tested for by numerical simulations. So now you can, well, from this part, the only thing that I want you to remember is that, well, we have developed this framework by enlarging the number of variables. We are able now to describe non-Markovian dynamics associated with aging. Maybe with more transitions, you can go to other non-Markovian dynamics. And for the case of the Granovetter-Batz model, what we see is that the only modification of aging is that exponential cascade going into a power law. So aging is now acting against consensus. Well, we at least had the opportunity to see that actually we can derive that this exponential cascade was turning into a power law thanks to the approximate master equation, and the results are published in this paper here. So that is why we went to study the third model for this part of the thesis, that is the symmetrical threshold model, in which I like to motivate with the following example. You remember in the COVID pandemic, in which the video conferencing apps were starting to grow a lot. For example, Zoom, that we have here, Skype, Teams, they were growing a lot. So for me, this is the perfect example to describe a situation in which the symmetrical threshold model occurs, because there was at the same time competition, but also innovation spreading through the system. So now in our model, what we will have is that agents can be using these two technologies, but they can, it's a symmetrical state. It's like the model that we had before, but symmetrical. Now, if you see a fraction of different kind neighbors exceeding your personal threshold, you will change state, and then you can go back to the previous state. And to this model, we will ask ourselves how consensus is reached, if it's reached, and which are the different phases of the model. Well, this actually was previously studied in literature by one of our jurists also here today, in which they were analyzing the symmetrical threshold model for thresholds above 0.5 and looking to the effect of the noise or the nonconformity. And they actually found that there is a presence of hysteresis. Well, some of the features that she was actually mentioning yesterday. Also, remember that for these rules of the symmetrical threshold model, for threshold equal to 1.0, what you have is that the update rules of the symmetrical threshold models are equivalent to the global dynamics of the Ising model at the limit of zero temperature. That is actually the majority vote model, which was actually studied under the effect of aging, also looking the influence of the noise in this article here. So there are some things done already in literature, but what we focused is on how the phase diagram of the model was, how was the phase diagram of the model for all the values of the threshold and also all the values of the initial condition. And what we saw is that actually for different graphs, for different networks, what you see is a similar phase diagram in which we have a phase 1 where the system is mixed, a phase 2 where the system is ordered, and a phase 3 where the system is frozen. Actually, it happens the same as for the Granovetter-Batz model. You cannot use heterogeneous mean field because it gives you descriptions of these lines here for the mixed to ordered transition, and it is not able to predict phase 3. But for the approximate master equation, actually, you can actually extract the transition lines, but just for obviously the case networks generated with the configuration model. And obviously, to analyze the phases, the first phase is characterized by this active mixed disordered state. Phase 2 is characterized by just majority wins. The majority in the initial condition will win, and this adoption becomes very fast. It goes very fast to consensus with an exponential decay of the average interface density. And for the frozen phase, it's similar to the ordered. It tries to order, but it gets frozen into an intermediate phase because the thresholds are so high, and since we are starting from a random configuration at a given magnetization, well, the system frozens at a certain state. Well, the motivation as before, we introduce aging into this model. Now we analyze how, well, just as before, we introduce this activation probability that depends on the time that you have been in your current state. But now, obviously, there is this competition. They can be in the time of one or the other. It's not just the non-adopters, because they get used to the technology that they have been using. And actually, it's a good scenario to test that you have now a lot more of transitions for the approximate master equation, and you can test if the framework actually works. And what do we see when we introduce aging into the system? Actually, the frozen phase seems to be the same. The system freezes at some point. The ordered phase is very similar also. Ordering majority wins, but now the exponential the exponential decrease of the average interface density is turned into a power law. So something similar to what we have seen in the Granovetter-Batz model. But now for the phase one, for low thresholds, what we see is that for 1,000 time steps, the stationary state was not reached. And actually, when you increase the time, what you see is that seems to be this phase one reducing from the limits as before. But actually what's happening is that phase one is no longer present. It is replaced by this phase one star, in which the system initially disorders, but then at some points, due to aging, it tends to order. So from an initial condition, it will go to magnetization close to magnetization zero, and then at some point, it will start to order. The same is happening here for the blue line that for the red one. But for the red, what you see is that actually for different values of the threshold, this interface decay becomes very slow, similar to logarithmic. So something very slow dynamics. And most interestingly, what we have here is that, well, from any initial condition, doesn't matter if there is a big bias in the initial condition, the system will go to the 50-50 situation, and then suddenly one of the two states will reach consensus. So now a minority will go to the 50-50 situation and then go to consensus. So a minority is able to reach consensus in this phase due to how we introduced aging effect. So actually we are introducing an effect of memory, but due to this initial disordering of the dynamics of the model, actually we have that the system is forgetting the initial condition, what actually can be counterintuitive. This can be also shown for many different topologies in the system. For Erdős-Rényi graph and random regular, this phase one is replaced by phase one star. But on the other hand, for the complete graph, we see that phase one is still present. But actually, one can go from this situation to the complete graph just by increasing the mean degree, keeping n constant. And this is what we did. We analyzed for two values of the initial magnetization, and this is the average degree versus the threshold. And at the beginning, we are in this situation in which we have phase one star turning into phase two. But suddenly, as you increase the average degree, phase one reappears in the system. You have at some point the three, phase one star, and phase two. But as you keep increasing the mean degree, phase one is the one that remains in the system. So actually, what you have is that this phase one star of initial disordering is a combined effect, not just from aging, but also is only present at the sparse networks. So the topology of the network also affects to this part. So just to recap, it's nice to study this symmetrical threshold model because it has all the effects that we have seen from aging in threshold model before. We have the Sakoda-Schelling effect of a mixed transition going to an ordered one, so promoting segregation or promoting ordering here, but also going against order because the exponential decay now is followed by it's transformed into a power law. And we could test also the approximate master equation that I have not said it, but in here, the approximate master equation are the approximate master equation with aging is the one, are the solid lines here, and the dots are simulations. And you see that it is able to capture these disordering and ordering dynamics, actually. So this framework seems to work here, and these results were published in this paper in New Journal of Physics. So now let's go to the second part of the talk, and that is the study of a real case scenario that is the housing market. In here, we have a real data set from the platform Idealista, that is the one that is most used in Spain for property rentals and sellings. And we have a data set of 2 years where we keep the location, the price, the square meters, the real estate agency that posted that listing in the platform. We don't have the full region of Spain. What we have are just 3 regions: Madrid, Barcelona, and the full area of Barcelona and Balearic Islands. And what you can see when you make a zoom to Barcelona, for example, is that actually what you have is a mess, something different, something very complicated to study. But what housing market has actually do with aging? Well, actually, we have the activations and the activation date of the ads, when they were posted and when they were unposted for the platform. So from So sold in this sort of sense, the listings were sold. Okay, and while you see that the number of total listings in the platform is increasing linearly with time, so ads are added at a constant rate, actually, when you look to the number of active listings, actually it shows more irregularities. We can observe a weekly pattern in the data, but also some irregularities, some peaks, and some valleys that remind us to the burstiness effect that we had in communication technologies. But actually, when one looks to the interactivation time here, distribution, the power law is less heterogeneous than the one we were seeing in the case of communication technology. While on the other hand, the listings life, what we call listings life, that is the amount of time a listing is on the platform posted, shows a fat tail distribution for the three regions that we have. As you increase the window of your observations, the power law is growing and growing. So we have a situation in which listings are added into the system at a constant rate, but actually they disappear after some time according to those distributions. So you can say that this kind of a phenomenon of aging, like the longer a listing remains in the platform, the less likely is to be sold. Obviously, this is a way of thinking about it, of modeling. Obviously, listings are in the platform because they want to be sold. But its aging can be understood as a temporal attractiveness of listings while they are in the platform. This process of particles created at a constant rate, but then decaying after some time according to a random variable with a distribution. It's already in literature. It's called delayed degradation, but it has just been studied for distributions of the time that are Poissonian, not for fat tail distributions. So actually, it's something difficult to treat. So, and to study now the dynamics of the market, what we do is that we will see each listing as this horizontal temporal line in which the color represents the real estate agency. This is the initial date of posting the ad, and this when it is unposted, it is deleted. And the metadata will be the location of the listing and also the price per square meter. So the platform, the market, in this sense, our proxy of the market, that is the platform, looks like something like this. With time, the different listings are appearing and disappearing. So what you can do is pick a temporal window, and now all the active listings create what is called a bipartite network, where they are connected to the real estate agency that posted it. And for a different window, you will have a different bipartite network, and you can compare them actually to try to explore the dynamics of the system. First, before comparing the dynamics, what we will do is to analyze how is the accumulate bipartite network and see if there is some natural spatial segmentation of the system due to how agencies interact in a space. So in this situation, we take the network, the bipartite network. Obviously, listings are posted in a certain location. We can do squared cells because we are physicists. We like squared cells. And we associate each listing to the squared cell where it belongs. Now, having this multipartite network, what you can do is just contract the number of listings in the platform, get a weighted bipartite network, and now the most complicated part of this project that is very simple, that is just we will project into a network of cells, but we are projecting not using the typical Jacquard index. What we will do is to project accounting for the influence of each agency at each cell. So accounting for how many listings has this agency, how it is working, to try to understand, well, how is the market in the different cells of the system. To understand this projection, and the best way is with an example. You can have the situation here in which you have two cells and two agencies working in both two cells. And as you can see, in both cells, the 99% of the listings is in cell I, and the 1% of the listings is in cell J. So actually, the way the two agencies that are present in the two cells, the way they work is the same. So the weight will be maximized. In the other hand, you can have this opposite situation in which, for example, now cell I is dominated by the listings in agency green. but now, and cell J is dominated by the listings in agency red. So now the market is set to be different and the weight is minimized. Obviously, if there are no common agencies between the two cells, the weight will be 0. There is no common market. But now, with this network defined, it's very simple that you can extract the natural partition of the market, just taking this network and applying community detection methods for, doing consensus clustering several times. And what you get is this partition of the market. And why do we say it's a natural partition? Well, actually, because we tested for many different community detection methods and different scales of sizes of cell sizes, and actually the partition is very similar for the different methods. So it seems to be some mechanism underneath that actually is creating this segmentation. And actually, when you look, is first that the nodes of the C community are clustered together spatially, that this is something not imposed in the way we constructed the network. And also it is respecting these, for example, the market on the islands is different. That is something that actually it makes sense and that we can extract with this methodology. And then we said, okay, this is happening in Spain, but could be happening something, could be something just from the Spanish market. Well, we went to analyze this data set from France, from the cities of Paris, Toulouse, and Marseille, the urban areas around those cities. And we had listings from the platform Celloguer, but actually the listings were at the census level. But we said, okay, you can do the same methodology, just instead of cells, you have the census where each of the listings belongs. Well, actually, we thought that the same could happen, but when you test this situation in Spain, when you are using census, actually the communities are not appearing anymore. While you use municipalities, this is similar to the case of the cells, to the community that we found in the cells. When you use census tracts, the results are not the same. And this happens because of how the census are constructed. But we developed a simple methodology. Well, the most simple thing that you can do is take the census, now divide them into squared cells, and you will assign stochastically each of the listings associated to one census to one cell with a probability proportional to the overlapping area between the census and that cell. So it's true that this is an stochastic process, but you can do an ensemble of many different networks, apply to them the clustering methodology, and then aggregate all together with consensus clustering into a single network. And actually, when you test this methodology in Spain, where we have the cells, the municipalities, and the census, from the census level data, you can reconstruct the communities with this methodology that we had in the municipalities or in the 1 kilometer cells. So actually, this seems to be working. So we can apply it into the scenario in France. And what we see is that the communities appearing show these similarities of being clustered together spatially. So actually, this effect, this housing market segmentation seems to be something that is happening not just in the Spanish market, but also in other countries. So something more universal. So, okay, there should be some mechanism underneath the data, underneath the dynamics that is leading to this segmentation. So we want to analyze the dynamics of the system. Now we will use the temporal part of the bipartite, not just accumulating it. And we will ask ourselves how listings are attached to certain agency, because the reason why a certain householder is deciding to choose a certain agency is actually the mechanism that is driving to how agencies will interact in the system. And the first thing that we observe is that as you go increasing the dynamics of the network, what you see is something that we are used to see a lot in network theory, that is the preferential attachment methodology. The more listings a platform has active in the platform at that precise moment, the more new listings will be attached to that certain agency. So more popular agencies will get more number of new listings in this sort of sense. Also, we can analyze the dynamics of the location. We can define the agency center of mass, so where an agency is behaving by just doing the center of mass of the different listings of a certain agency active listings that are posted in the platform, define the radius that actually looks like something like this, where the agency center of mass is the center, and the radius is, well, the radius makes the circle, and you see that there are very small agencies, but also very large ones. And regarding to the dynamics, one can see that there is some kind of specialization behavior. So on average, new listings attached to agencies that have a radius larger than the distance between that new listing to the agency. But that radius was computed, obviously, before the listing was posted by the platform, so before the attachment. So there is some kind of regionalization effect. Also, you can compute the logarithmic difference between the distance from the new listing to the agency center of mass and the radius, the effective radius of the agency, and see that it follows a t-student distribution centered at negative values, obviously, because on average they fall inside the radius, but sometimes it also falls outside the radius. And the third mechanism that we have is regarding to the price. That is something similar. When new listings are posted into the platform, they are posted by agencies that they have a similar mean price. The mean price of the real estate agency is similar to that new listings price. You can also compute the logarithmic difference between this price of the new listing and the mean the mean of the logarithm of the price of the listings on that agency, and see that it also follows a t-student distribution, but now centered at 0 due to this price similarity mechanism. And what are those? Well, these mechanisms at the end are the ones responsible on how the listings get attached into a certain agency, so leading to the segmentation that we see, but also to this degree price correlation that we can observe in the accumulated network. This is the average degree to the mean price of the agency, and you can see that there is some segmentation because we have here low agencies with a low mean price that they have a few number of listings in the platform, and they are all the distributions of the price of the agencies are actually Gaussians, similar to normal distributions centered at low prices. We have the generalist agencies with a lot of listings in the platform, and they actually have a lot of listings at average prices. But we also have the high prices real estate agencies that they also have low number of listings, but they don't have actually distribution centered at high prices. What they have are some listings at high prices, but also a lot of listings on average prices that you can see, because that is why this is actually having a much higher variance of the price of the listings of a certain agency. So just a recap of this part, we have seen that the real, regarding to the listing dynamics, we see that there is this kind of temporal irregularities that could be modeled with these ideas of aging, can be thought in this sense, but to extract and also that one can study the housing market just using this temporal bipartite network setting in which you can extract the static properties, the segmentation that arises in the system, and also dynamic properties. These three mechanisms, popularity, price similarity, and spatial specialization, that is driving the dynamics of the system, this decision-making mechanism that householders have. The first part of results are available in arXiv, so we can go just to the end of the presentation, to the conclusions and the further work. Well, from the first part of the thesis, we can conclude, we have analyzed how aging actually affects the different thresholds of collective behavior, threshold models of collective behavior. But we have seen that there are many different effects. You see that aging is favoring segregation, but on the other hand, you have a contagion model, and now it is able to change this exponential cascade to a power law. And now that we have the full picture, we can understand the effect of aging in threshold models. That is actually just that aging is a simple but complex mechanism that prevents small clusters to dissolve. It's just that, because in a mixed situation, this preventing small clusters to dissolve is what is driving the system to a mixed active disordered state to consensus, because clusters are starting to grow and grow, and the aging will prevent, as they grow bigger, it will be more difficult for those clusters to dissolve. But on the other hand, when you have a drift towards order and ordering dynamics, what aging is doing is just this minority to, preventing this minority to dissolve. And that is how you can understand that is actually promoting order. It's not promoting order or promoting disorder. It's just that it's preventing a small cluster to dissolve. And with this idea, you can just understand everything. Regarding to the second part of the talk, you can use this bipartite temporal network approach in order to address the dynamics of the system and address the static and dynamical properties of online listings. From the first part, I want you to remember that this is actually a general methodology. If you have geolocalized data with some particular metadata that for us was the real estate agency, but actually you could use anything. If you had geolocalized data with any particular metadata, you can use this methodology to assess if there is segmentation. And also we have this bipartite projection in which you go from a weighted bipartite into a weighted simple network that actually is something that is very general, and preserving the weight is something that was not that present in literature. And regarding to the second part, how the dynamics of the market, saying that the dynamics of the market are governed by popularity, price segmentation, price similarity, and spatial specialization is an important claim. We obviously need more data and more analysis to extract that, but at least it's a quantitative analysis that we see these effects from correlations. And it is always said that the three things that matter in property are location, location, and location. Well, actually, we have seen that popularity, at least in online portals, is something important too. And just to finish, some further work that one could do is analyzing the idiosyncratic behavior, the independent behavior, introducing aging into this part. Obviously, there is a lot of work done with independent behavior, but it makes sense that as an agent gains confidence in something with an idea, this random swapping of your state, of your opinion, becomes rare. Also, obviously, validating these ideas of aging and memory by conducting experiments with human subjects or collaborating with psychologists or sociologists is something very important. So, and see how persistent time correlates with how the decision-making process is done. Well, this is another further work that one could do that is actually me, the one that is doing it, that is constructing a model based on these ideas of aging and incorporating the three mechanisms described. See if we can make a model that can describe these degree price correlations or the spatial segmentation. This is something that we are doing now. And maybe even if we could make some general equation on how the bipartite network is evolving, it could be great. And at the end, just explore the generality of our findings. For example, for the segmentation of the market, we have a data set of 3 regions. In 2 countries, it's true, but what would happen if we would have the full country or a continent level data? Well, those communities will still be there or will be part of some bigger communities. And just to finish, thank you to everyone that gave me support during this thesis, economically or emotionally. Thank you. This is everything that I had to say for today.
Thank you, David. We won't applaud at this point as the exam is still in progress, but thank you for the talk. We are about to move to the next portion of this examination, which involves questions from the committee. Just before we do that, I can offer the opportunity to exit if people would like to leave the room at this point. The questions of the committee will be rather extensive, so you may wish to take the opportunity. Thank you.